Welcome to Pomodoro Joe for Wednesday, June 7th, 2023. Today we're doing LeetCode problem 1318. Minimum flips to make A or B equal to C. This is a medium problem. Given three positive numbers, A, B, and C, return the minimum flips required in some bits of A and B to make A or B equal to C. Bitwise OR operation. The flip operation consists of changing any single bit from 1 to 0 or change a bit from 0 to 1 in their binary representation. Then they have an example here. So they've got 0010, which is A, and 0110, which is B. And we're trying to get those to equal 0101, which is C. So it looks like we need to flip 2 bits here and 1 bit here. So that should be 3. Yep, 3. Okay, pretty straightforward. So with that, we'll put 25 minutes on the Pomodoro timer and we will get started. So for this one, I'll do this the straightforward bitwise operation way. And if there's time at the end, we can check out some more fancy sort of ways to do it. So for this, we need to know a couple of things. First, we need to know what bitwise or bitwise operations are. We'll also need to know how to mask bits, or what bit masking is. So I'll explain those first. So you're probably familiar. If you already are familiar with this, you can jump ahead and get to the coding. If you're not, then you can stick around and I'll go over these bitwise operators. So you're probably familiar with logical OR. So if I had A, let me do some space here. A or B, then we have some result. All right. So you know that A or B, if A is false and B is false, then the result will be false. So we'll just go through some of those here. So if A is false or B is false, then our result will be false. Same thing down here. If A is false but B is true, then our result will be true because B is true. Because it's A or B, then we'll have true. If A is true and B is false, well then we still have true because A was true. And finally, if we have A is true and B is true, then our result is true. So that is the OR operator. So here they're telling us to do a bitwise OR operator. So we'll go into what that means. So the bitwise OR operator is going to look at the bits of A and the bits of B and do an OR operation on just the individual bits. So we'll look at the first bit of A and the first bit of B, do the OR, and that will end up in the resulting value, I guess. Then we'll take a look at the second bit of A and OR it with the second bit of B, and then third bit of A, third bit of B, so on and so forth. So a bitwise OR. Let's write this down here. That will be this pipe symbol. So this is the bitwise OR. And we basically go through and change all these falses to zeros and trues to ones, and that will be our truth table. So let's change this here. So false gets changed to 0, trues get changed to 1. All right, so this is what they call the truth table. So for this, we have A or B. So both are 0, the result is 0. If either one is a 1, the result is a 1. Or if they're both 1, the result is a 1. Now we can do something similar with A and B. Now the bitwise AND is this ampersand symbol, and it's just a single ampersand symbol. So if we did A and B, well, if they're both 0, we'll get 0. Now, if either one is 0, so A and B, if either one is 0, then the result is also a 0. It's only when both A and B are 1s that the result is a 1. So that's how we do bitwise operations. That's the OR operation and the AND operation. And I'll go through one more operation really quick you don't need to learn this one, but it is useful to know. So there's something called an exclusive OR. So that's this little caret symbol. Looks like a little pointy arrow pointing up. So the caret symbol is a bitwise exclusive OR. And what the exclusive OR does is it's just like the OR, except it's only true if either A or B is true, but not both. So our regular OR, we had basically this. So with the regular OR, if either A or B or both are true, then the result will be true. With the exclusive OR, it's only when exactly A or B is true that this will be true. Otherwise, if A and B are true, or ones, then this will be a 0. So that's the exclusive OR. Now that comes in handy later on, but we won't actually need it for our initial solution. Now finally, we'll go through some bit masking. So what bit masking is creating a mask. This is similar to if you've ever done stencils or masking tape when you're painting. This is a way to what they call mask out some bits. So you select just the bits that you're interested in, and you can ignore all of the other bits. And the way a mask works is you create the mask. So we'll create something like a mask. And we'll give it some bits. So we'll say 0, 0, 0, 0, 1, 1, 1, 1. And anywhere that we have a 0, those bits will be ignored. Anywhere that we have a 1, those bits we'll take those bits into account. So if we were to take, let's say some number, let's use maybe one of these example numbers over here. So they have 0, 0, 1, 0. So if we have A, and that's equal to, this is the bitwise value, 0, 0, 0, and we have 0, 0, 1, 0. When we mask this, well, this is a bad example because when we mask this, we'll get exactly A back out the other side. So when we do a mask, we will do an AND operator. So our mask, so we will do A and our mask. And in this case, well, we'll just get A back out because these zeros will mask out these zeros and A will come out the other side exactly as we put it in. Let's try a better example here. So let's do A is equal to 1, 0, 1, 0 and 0, 1, 1, 0. If our mask, I'll do this. If we had our mask of all ones, then what we get out the other side will be exactly what we put in because we're not masking anything, we're keeping everything. There's nothing actually being masked out. So we'll get 1, 0, 1, 0 and 0, 1, 0, 1, or 0, 1, 1, 0. So that's with this mask. Now what if we decide to change this mask? What if we did 0, 1, or what if we did this? We want to mask out these middle bits. Well, when we do the AND, this 1 and this 0 will become a 0. And so we'll end up masking out this bit here. And this will be our result. Now let's say we only care about these lower 4 bits, so we can change our mask to be all zeros at the top. Then on the other side, anything masked with a 0 will be a 0 because we're doing an AND operation. And this is what we'll end up. We'll just get the lower 4 bits of A. We'll end up with zeros in the lower 4 bits of A. Now let's say we only care about the last bit of A. We'll add this. Our mask will mask out everything except the final bit. And in that case, we will just get this. We will get 0 and 1, which is a 0. So that's how we do a mask, and we'll be using the mask a lot in our example problem here. All right, so let's get to it. So we have some result. We'll set it equal to 0 to start, and at the end, we will return our result. Now for this, I want a mask to just look at the last bit of A, or you might call it bit 0 of A. So our mask will just be, well, it's 0, 0, 0, 0, 0, 0, 32 zeros and a 1. You can actually just say it's a 1. So this will be all zeros with a final bit that will be a 1. Now in other languages, you might have to make your mask a little bit more explicit, but in Python, I can do this, and this represents 0, 0, 0, 0, 0 with a single 1 bit at the end. Okay, Now our problem here is to find out how many bits we need to flip to make A or B equal to C. So let's just say, well, A or B is not equal to C, well then we need to do something. Now I don't actually want to modify this A or B directly here. So in this case, it doesn't really matter because these are not passed by reference, but I want to keep track of my own internal A or B. So I'll have a remaining A. So this is what's left of A, and I'll have a remaining B and a remaining C. So what I'll be doing is I'll be masking out my A, my B, and my C, and I'll be comparing them to each other. So I'm looking for every place where A and B, or A or B, when I mask those, they equal C. If they don't equal C, well then I know I need to flip some bits. All right, so we will do a mask, we'll do a comparison, then we will shift all of our bits. So we'll constantly be shifting our bits to the right. So we're always looking at just the last bit, but we'll shift all our bits to the right. So we're essentially going through every single bit in our A and B. Okay, so while A or B doesn't equal C, but now it's the remaining A and remaining B not equal to remaining C. Okay, so in Python, I could just use A, B, and C. In some languages, the inputs are immutable, and so that's why I'm doing it this way. We're just going to show you that we have to keep track of these changes to A, B, and C. So we have a remaining A or remaining B. This is the bitwise OR. If it's not equal to the remaining C, then we need to keep going. So what's the first thing I'll do? I'll check the remaining A and our mask against remaining C and the mask. Let's see, and our mask, that doesn't equal remaining C. So let's see, this is a little bit tricky because just checking that remaining A and the mask doesn't equal remaining C and the mask doesn't necessarily mean that I need to flip the bit, because if A is a 1, or let's say A is a 0 and C is a 1, just because A and mask doesn't equal C doesn't mean that B in the mask doesn't equal C. And A or B, if B is a 1, so if A is a 0 and B is a 1, we might be able to still get A or B equal to C in that case. So let's actually do this a little bit differently. Let's check out if C is a 0 first. So let's just find out, what is C? So if the remaining C and the mask is equal to 0, well now we know we need both A and B to be equal to 0. So the way that the OR works, if either A or B is equal to 1, we'll have to flip that bit. If A and B are equal to 0, well then we're okay. So we'll just check both A and B against 0 now. So if our final bit of the remaining C is equal to 0, well then we need both A and B's final bits to be 0. So if they're not, well then we need to flip them. So if remaining A and mask doesn't equal 0, well then we need to flip that bit. So result plus equals 1. And we'll do the same thing with B. If the remaining B and mask doesn't equal 0, well then we'll need to flip that bit. So that's if our remaining C at the final bit is a 0. Now, if it's a 1, that's a different story. So if remaining C and the mask is equal to 1, well in this case, if either A or B is a 1, then we can just use that. We don't need to flip any bits. It's only when both A and B are 0 that we need to flip one of the bits. We don't need to flip them both. So we can just check if the remaining A and remaining B, or we could actually say or remaining B. There we go. If remaining A or remaining B is equal to 1, then we don't need to do anything. But if it's not equal to 1, then we need to flip that bit. So our result plus equals 1. All right, and now we need to update our remaining values. We need to shift all of these remaining values by 1 bit. So remaining A becomes remaining A shifted to the right by 1 bit. I didn't talk about this shift operator, but you can check that one out. So we're going to shift our remaining A to the right by 1 bit. And we have to do the same thing with B. and the same with C. And I think this should do it. Oh, I forgot to mask this. So we still need to do a mask here. So the remaining A or the remaining B will be could be a large number. I still need to mask out just the final bit. All right. And we pass. We don't do very well. We only beat 6% for runtime and 25% for memory. So let's jump back in here. One thing we can do is we don't need to do this if. We could have an else here. That might save us a little bit. And we can close up a little bit of this space here. This is just some formatting stuff, but it does actually help. I wouldn't necessarily recommend doing this for real production code just because it's not quite as clean, but it does work. All right, try that. Hoping to get above 10%. Oh, that's much better. We get a 59% for runtime and a 68% for memory. So yeah, that's a way better solution. It's amazing what a little bit of an else will do here. Okay, so this is our main solution. We're using masking, we're using bitwise operations, we're going through every bit, checking it against C, and we can get our answer. Now there's one other way we could do this. Well, there's a couple other ways we can do this, but one other way I'll go over super quick. Oh man, there's not a lot of time. So one thing we can do, this has to do with those truth tables. If we do an A or a B, or an A and a B, so the A or B's will basically let all the ones fall through to our result, and only the, how do I explain this? In the result of an A or a B, anytime you have a 0, it's only because both A and B were 0. Anytime you have a 1, it's because either A or B or both were 1s. So if we look at our A or B and compare it to our C, any place that we have zeros in A or B and a C, then we're all good. A and B were both 0, C was 0, that's exactly what we want. Anytime A and B are a 1, and C, or I should say A or B are a 1, and C is a 1, well that's also okay, because A or B, we don't know which one was a 1, it doesn't really matter. As long as they match what was in C, it's all fine. But if we have A or B being a 1, and C being a 0, that's where we have a potential problem. Also, if we have a C being a 1 or an A or B being a 0, that's where we have a problem. So let's write this down. I'm going to run out of time on this. So if A or B is equal to 1 and C, and C is equal to a 0, well then we need to flip some bits. We don't know if it's 1 or 2 because we don't know if it's both A and B being 1 or if it's just A being 1 and B being 0. So anyway, this does mean that we need to flip. So I'll say needs flip. Now if we have an A or a B and that's equal to a 1 and C is also equal to a 1, no flip, because that's what we want. We were trying to get A or B equal to C. So if A or B is equal to 0 and C is equal to 0, also no flip. Now if A or B is equal to 0, but C is equal to 1, so if A or B is equal to 0, but C is equal to 1, we need a flip, needs flip. But we only need to flip one bit, either A or B. So let's see, what's our truth table here? Let's take a look at these zeros and ones. All right, so we have, I'll call a needs flip as a 1 and a no flip as a 0. Okay, so let's see, needs flip is 1. No flip is 0. Needs flip is 1. Oh, sorry, this is a no flip. That's a 0. And a needs flip is a 1. Okay, so we have 1, 0 is a 1. 1, 1 is a 0. 0, 0 is a 0. And a 0, 1 is a 1. So this looks a lot like our exclusive OR. If either A or C are 1, but not if both are 1. Do we get a 1? So this is A or B exclusive ORed with C. That will tell us which bits need to be flipped. So we can use A or B exclusive or C. Now, the problem there is we don't know when, if it's, let's see, if we have this one, A or B is equal to 1, we don't know if it was A equal to 1 or B equal to 1 or both equal to 1. So we might need 2 flips here. So this is where it's going to get a little bit confusing, but we can start with this. So I'll do a flip count here. So it's going to start out with, we have A, and we do an OR with B, and then we'll do an exclusive OR with C. So this tells us that we need at least that many flips, but we might need to do more because we might need to flip both A and B back to a 0. So that's the case where we have A and B both equal to 1, but we need it to be a 0. So how do we find out if A and B are equal to a 1, but we need it to be 0? Well, that's where we get a little bit more confusing here. So I don't have enough time for this one. Well, I'll just write it out and you can try this on your own. Okay, so you have an A and a B. So if you do an A and a B, this will only be 1 where both A and B are 1. So that's going to give us only the bits where both A and B are 1. Now if we compare that, if we do an AND with not C, so a not is this little tilde thing, so that will flip all the 1s to 0s and all the 0s to 1s. So if we do an AND with not C, that means all the places where we're expecting a 0 will become a 1. And so now both A and B were 1, and all the 0s are 1s. This will give us a 1 anytime A and B and C was a 0. So this tells us how many additional bits we need to flip. So we basically need to do a flip count for this plus this. So I'll call this like flip count 1 and flip count 2. And we are going to run out of time, but I will push through and I will show you the end here. So now we have to count the number of bits. All right, I'm just pushing through. We'll just wrap this up really quick. So now we do have to count the number of bits left in these flip counts. Now there's a couple different ways we could do that, but let's just do it this way. Maybe I shouldn't have called it flip count. Maybe I should have called this like flip mask. Oh, that's right. So to find the number of bits, we'll do basically what we did before with our looping and our shifting and our mask. So we still need a mask. There's other ways to do this, but this is sort of the straightforward way. All right. All right, so while we have either flip count 1 or 2, we'll basically be doing a mask, we'll be doing an add to our result, and then we'll be shifting. So our result plus equals the flip count, a 1, and we'll mask, so we get either a 1 or a 0. And we'll have to do the same with flip count 02. And then we'll need to shift both flip count 1 and flip count 2. Let's see, I'm gonna try, I don't know if I can do this. Shift equals 1. We'll find out if that works. Okay, so we're going to do 2 different flip counts. One will grab all of the places where A or B are 1, and we're expecting a 0. Or all the places where C is a 1, and A or B is a 0. Then we'll have to fix that up by doing this additional A and B, so find all the places where A and B are 1, but we were expecting a 0. So that's basically we grab, how do I put this? All the places where A or B had been a 1 and we're expecting a 0. We definitely have to do 1 flip. We might have to do 2 if both A and B were 1. So this is going to basically patch that up, give us that extra flip if we need it. All right, go through, do the flips. All right, let's see if this works. And it works. Let's submit that. This might be a little bit faster than our other solution. And it's not. This only beats 8% for runtime, 68% for memory. So this actually isn't that much faster. A little bit surprised by that. but it could be this part. This isn't super fast. So anyway, you could do a lot of stuff in here to clean this up. You can make this one, I guess one equation, but I am way over time. So that is it for me. All right. Hope you learned a little bit about bit masking. Hope you learned a little bit about bitwise operations. Yeah. Hope you had fun with this one. All right. Hope you enjoyed this. Hope you had fun. Hope you learned something. Hope you can go out and write better code.